So ultimately, we want to use cohomological dimension to study algebraic number theory and algebraic geometry and so on. So we want to look at cohomological dimension of groups associated to fields, in particular Galois groups. Remember previously we defined for a field K, the pth cohomological dimension of K is just that of its absolute Galois group. So what can it tell us about the field K? Well, if the characteristic of K is not equal to P, then this tells us quite a few things. It tells us about the Brauer group and the relative norm groups of extensions of K. However, if the characteristic of K is equal to P, then this doesn't tell us really anything, because all of the field K's with characteristic P has pth cohomological dimension less than or equal to 1. We'll prove this in the next videos. For now, let's just consider the case when the characteristic of K is not equal to P. We will prove that the following are equivalent. Let's start with 1 implying 2. So we let L be a separable algebraic extension of K, and we suppose that this pth cohomological dimension of K is less than or equal to 1. We want to deduce that the P primary part of the Brauer group of L must be 0. So here we want to use two ideas. One is the cohomological description of the torsion subgroup of the Brauer group, and second was the lemma on the cohomological dimension of subgroups that we mentioned before. So let's start with the latter. So we claim that from our discussion about cohomological dimension of subgroup, I should have that the cohomological dimension of L is less than that of K. And that's because the absolute Galois group of L is a subgroup of the absolute Galois group of K. And remember, these cohomological dimension, are just defined to be the cohomological dimension of the absolute Galois group. Okay, so we have that the pth cohomological dimension of L is less than or equal to 1. So what does that mean? That means, in particular, that the P primary part of the second cohomological group of L always vanish. In particular, the cohomology of L with coefficient in the roots of unity of order p to the I should have 0 P primary part. But from a previous result, we know that this is just the group of p to the I torsion of the Brauer group. And so, by the way, the primary part of this is just equal to itself. So this is equal to the p to the I torsion part of the Brauer group. Thus, the p to the I torsion part of the Brauer group vanish, and this is true for all I. So then the p primary part of the Brauer group must vanish, and we're done. And so how did we know that the M torsion part of, say, the Brauer group would be isomorphic to H2 with cohomology in mu M? Well, that comes from looking at the long exact sequence associated to this sequence. The short exact sequence associated to the map X maps to X to the M, the power map. And then we need to use the cohomological characterization of the Brauer group. Thus, we have proven 1 implies 2.